Hi, today we're going to do a problem on energy conservation and work. So this is a medium difficulty problem, I'd say. Something in between a basic C level and an A level difficulty. So what do we have today? Our problem. A truck is traveling at 11.1 meters per second down a hill when the brakes on all four wheels lock up. So it starts skidding. The hill makes an angle of 15 degrees with the horizontal. The coefficient of kinetic friction between the tires and the road is 0.75. How far does the truck skid before coming to a stop? All right, so typical problem solving. Start with a picture. Truck traveling down a hill. Okay, so here's my truck. Very fancy. It's moving to start with. And now remember, with energy problems, it's not just a picture. We need a picture for the initial and a picture for the final condition. So my initial condition, my before, is going to be at the top of the hill. It's moving. And my final is going to be some distance down the hill, not moving. It's skidding to a stop as we go down. So there's my basic picture. And sometimes what I'll do when I do the picture is just remind myself, this is initial and this is final. Okay, so now we go to our knowns and unknowns. We had an initial velocity of 11.1 meters per second, and the hill makes an angle of 15 degrees with the horizontal. All right. The coefficient of friction was 0.75. That's all we're given. We're not given mass. How far does the truck skid before coming to a stop? So we want to know the distance it travels down the hill. So I'm going to say my D, distance down the hill, is what I'm looking for. Picture, knowns, unknown. And now what we typically do in energy conservation problems is I want to start with the energy conservation equation and then see if I have to go into forces to figure out my work and see what else I might need to do. So initial energy plus or minus work equals final energy. Now, if you're comfortable with thinking of the three types of energy yourself, then you could just kind of jump in there. If you're still trying to figure out, okay, what type of energy is there? What you might want to do is write down all three types of energy and then say, okay, is there this type of energy? Is there that type of energy? So you could also write the same equation as that top one, like this. Just reminding yourself, we're dealing with three types of energy. So we could have, initially, we could have kinetic, spring, or gravitational. At the end, the final condition, we could have kinetic, spring, or gravitational. So if you're still struggling with writing this equation, the conservation of energy equation, then try doing this and cross off the ones that aren't there. So the questions to ask yourself for kinetic energy, is something moving? In our initial condition, is something moving? Yeah. We definitely have that one. So we have kinetic to start. Is a spring compressed or extended? Well, there's no spring in this problem. I'm not worrying about that. For potential energy due to gravity, the question to ask yourself, is something above its lowest point? I'm starting here, I'm ending here. It is starting above its lowest point. I do have PEG to start with. In my ending condition, same three questions. Is something moving in the final state? Nope. Is there spring? No. Is something above its lowest point in the final condition? No. Okay. So if we simplify that down, the equation that we end up with, the conservation of energy equation for this problem, looks like this. We have kinetic energy to start with and potential energy due to gravity to start with. We end with nothing. And then I say, well, something clearly had to do work on this. If I start with something and end with nothing, I had to subtract something. So something did negative work. And here's where we say, what did work on it? Okay, go to your force diagram. So what does the force diagram look like in between these 2 points? I'm at an angle, drawing it at an angle. I've got my normal force. I've got a force of friction, slowing me down. Gravity acts straight down. The Earth is pulling straight down on us. And that's it. There's no longer any forward force on the truck, so there's nothing pushing forward except gravity. And now here's another thing I often do with work and energy problems is I remind myself what direction the motion is. So D is going like this because the only forces that do work are the ones that are parallel to the direction of motion. So if D is like this, sometimes you can grab a ruler and take a ruler and just say, okay, if D is like this, are there any forces that line up? Well, clearly that one lines up. So the friction force is going to do work. So I know I've got that one to start. And I've work done by friction. And it's negative because direction of motion is this way, friction force is that way. Anti-parallel means negative work. So it's taking away energy from the system. Is there another work term? Well, here's a subtlety. There is a portion of gravity, the force due to gravity, that is parallel. So if I break this vector up into a component this way and a component that way, I do have a parallel component. Now I'm not going to say that's work done by gravity because I already took into account gravity right here. I'm dealing with gravity in this term right here, so I don't have to double count it by saying, oh, and there's work done by gravity. So if you were to add a little work term, positive work done by gravity, you would be double counting the work done by gravity or the energy from gravity. So don't double count gravity. You only want to include it as an energy term, not a work term. And the same is true for springs. Don't ever deal with the work done by a spring. Use the energy stored in a spring. So I'm going to get rid of this one. Okay, so here is my conservation of energy equation for this problem. And if you can get to this step, that's one of your objectives. So being able to write that for each problem is one of your objectives. So now, what are we looking for? We're looking for D. Where is D hiding in this? Let's write down what each of these three terms will be. Kinetic energy, 1/2 mass velocity squared. Potential energy due to gravity is mass times gravity times height. The work done by friction, negative, it's the force times the distance over which it acts. All right, so there's my term. Yay, I have a D. I want to know this. Okay, so I have 1/2, don't know mass, okay. I do know my initial velocity. I don't know mass. I know gravity. Don't know my initial height. And I don't know friction. So you might stop and say, how the heck am I supposed to solve this one? Okay, let's just take it a step at a time. Do we know any equations that will help us with any of these? I look at this whole thing and I say, okay, I have an equation for friction. So the fun equation, F equals mu n. So let's replace that F with mu times n. So this term is mu times n times d. I do know my mu, but I need to know my normal force. All right, how do I figure out my normal force? Back to the forces. So your force diagram right here is going to help you figure out what the normal force is in each problem. Don't fall into the trap of thinking that the normal force is always mg. That's a really common mistake. Anytime you're at an angle or if you have other forces besides like friction and normal, if you have any pushes or pulls, normal is probably not going to be equal to mg. So look at this and say, what's going on? Is there any acceleration in this direction? No. My acceleration is actually this way. So there's no acceleration up-down, which means that my normal force upward and this component of gravity downward have to be the same. And if you draw your triangle for your gravity force, the force of gravity, draw it like this, where you drop it down from the normal. This up here, that's the angle of the incline. So I can say that this up here is theta. And my normal force has to be equal to this side. So my normal force up and this side down have to be equal. The force is mg. This is the side adjacent to the angle, so that is going to be my cosine component. So my normal force I can replace with mg cosine theta. And we did this a lot with forces. But now I don't want to lose that mu out front, and I don't want to lose that d on the back. Okay, so that whole term expanded to that. Let's see what else we're missing. So 1/2 mv initial squared plus mgh minus the work done by friction. So kinetic, PEG, work done by friction. So I know 1/2, still don't know mass. I know v initial, don't know mass, g, don't know h. I know mu, I know g, I know theta, and I'm looking for d. But masses will cancel. There is a mass in every single term. I have 3 terms. I have a mass in all 3 terms, so my mass does not matter. Okay, good. We got rid of one thing that we don't know. The other thing we don't know is my height. I'm looking for d. I need to know my height. Okay, how can I figure out the height here? Well, I'm going to draw a new triangle. Let's see what we've got. So my distance is this along the hypotenuse of this triangle. 15 degrees from horizontal. This is going to be my height. Okay, I can relate h and d together with, let's see, opposite and hypotenuse with the sine. So the sine of 15 degrees will equal opposite over hypotenuse, h over d. I'm just going to bring that d up to the other side. H is d sine 15. You might say, well, I don't know d. That's okay. It's okay. We'll make it work. This is actually good because we got rid of one of our unknowns, h, and we're replacing it with one of the things we're trying to solve for. So it actually does help us to do this. So I'm going to rewrite that bottom equation now with the h replaced by d sine theta. I'm going to switch to a different color. So I've got 1/2 initial velocity squared plus g, and now I'm replacing h with d sine theta, okay, minus mu g cosine theta times d equals 0. And losing this d right here is a really common mistake, so don't forget to keep that d in that term. If it's just this, it's a force. If you add the d in there, it's a work, and we need work in this. Okay, 1/2, I know that. I know velocity, I know g, I don't know d, I'm looking for d. I know theta, okay, I know everything but d. It is solvable at this point. So I've got 2 terms with the d and 1 term without. Get everything with a d on one side. So 1/2 initial velocity squared equals, bring that over, it'll be a positive mu g cosine theta times d. Bring this term over, it'll subtract minus g d sine theta. Okay, and I'm going to factor out a d on this side. Mu, I got to keep track here, mu g cosine theta minus g sine theta, okay, equals 1/2 initial velocity squared. Okay, I'm getting closer. So I know everything on this side, and I actually know everything in the parentheses. So if I can get this erased, I can solve it. So at this point we have all the numbers, and it's just a question of solving for d and seeing if it's reasonable. Oh, okay. This is taking a long time. That's one advantage of the whiteboards, I suppose, is they erase better than this one. Okay, numbers. 1/2 11.1 squared equals d mu 0.75 times 9.8 times cosine, this is a big parentheses, cosine of 15 minus 9.8 times the sine of 15. And it never hurts to just verify that you have all your terms, 2 terms, okay, d mu g cosine theta, g sine theta. It doesn't hurt to do that with these. There's a lot of things in here. And if you do that, you can solve for d, and I get 13.5 meters. So that's about 45 feet. Is that a reasonable answer? 45 feet to skid to a stop? That seems quite reasonable to me. I mean, if you think about skid marks on the freeway, they're not usually that long, but we're going downhill on this one. This is like 25 miles an hour or so. So I would say that's a very reasonable answer. We've got it all. This was a complex one, if you think about it, because we had to do the force diagram, we had to do work, we had to figure out what our normal force was, and we had this extra piece where we had to relate one unknown to another unknown. And so that was another extra piece that we had to think about. And that I know people will struggle with. It's like, well, I don't know H. How can I solve this? I don't know H and I don't know D. I can relate the two. And so when I put that in, I now have an equation with just one unknown. So I think we've got it. Good job.